Good morning, good afternoon, good evening, everybody. This is the IEEE San Diego big chapter SSCS, CAS, MTT, APS, and EDS. So we hope to start our live events in the next month or so. And we are honored to host Professor Molnar. And this talk about N-pass mixers, simple circuits, surprising capabilities, and we are very happy to have him with us today. A quick introduction about Professor Molnar. He has his PhD from in electrical engineering from University of California, Berkeley. He also have industry background in RFIC group with Connext Systems, Newport Beach, California, and he has like a very solid theoretical and practical like background, and he has also worked on image processing, RFIC design, image sensors, neuroscience, and neural interface systems. Really, he has like very like solid background, and we are happy that he is with us today. And he is also a solid state society distinguished lecturer. And with that, we would like to thank him, and he can go through his talk. Thanks.
Thanks, Mohammed. So as the title says, today I will be talking about N-path mixers, simple circuits, and surprising capabilities. So I'll just dive right in. And what we'll do is sort of midway through the talk, I'll stop for a little bit and we can take questions. So that way you don't all have to sit here listening to me talk for an hour straight. Okay, get it working here. Okay, so the motivation that got a lot of us into the space of N-path mixers was a fundamental tension in wireless receivers, which is that in a crowded spectrum, your ideal transceiver would do two things. It would both resist interference from other signals at other frequencies, but also be able to use any piece of available spectrum by tuning to that spectrum. And these two requirements are sort of in tension. So the first requirement needs a reasonably high Q filtering to suppress out-of-band interference. That's straightforward. We've been doing that all along in all of our radios. But the second requirement means we need to be also flexible. We need to be able to change our center frequency and also our bandwidth sort of responsive to what's available in the environment or what we're assigned as time goes on. Now, parts of that are not hard. Shifting your local oscillator or shifting your baseband bandwidth on the flies is not a particularly difficult thing. We do that for a long time. But combining them entirely requires that you either have a large bank of filters to get that filtering, or you have some sort of highly flexible, high Q effective bandpath filter, which is hard to build. And so it turns out that N-path mixers and filters are exactly the kind of technology that can address this need. So that's what got us into it. And as I'll mention a little bit later, there's a whole variety of ideas that have sort of come out of this core capability. Now, just to introduce what a CMOS N-path mixer is, it's a passive mixer. It's actually very similar to a concept called the N-path filter, which has been around for longer than modern integrated circuits have been around. It was first introduced in the 1960s and has sort of seen periodic sort of rediscoveries over the years, with the most recent round of rediscovery happening about 10 years ago, maybe 12 years ago, when several ISSC talks happened that sort of brought this forward, and it's really taken off since then. It has some nice capabilities. It translates impedances and signals in frequency, and is actually a very simple switching circuit with some subtle behavior. So in the context of RF passive mixers, of course, these have been known for a very long time, but they become really important in the last decade or so, especially when you have 4 or more phases in a pulsed LO. And it really takes advantage of scaled CMOS. And so the pulsed LO is a critical piece to this. And I'm just showing what I mean here. Here, the local oscillator signals are for a 4-phase case, or 4 distinct 25% duty cycle pulses spread across 90 degrees phase shifts to give you quadrature. Now, just to give the big takeaway of why people have become so excited about these relatively simple circuits is it's a relatively simple circuit. It's just a bank of switches or transistors, but loaded by a low-pass impedance typically. So if you load this by low-pass impedance, that of course gives you low-pass filtering on the output. But the interesting property of these switches or these circuits, when done right, is they also upconvert that low-pass filtering to a bandpass filter centered on your local oscillator. And this is due to a property that we often call impedance transparency. And this means now that if I have an out-of-band voltage signal coming in, of course, at the baseband side, it gets suppressed by the low-pass filter, but now it also gets suppressed on the RF side. And so therefore, the whole circuit is protected from the large amplitude signal and therefore has a much better linearity. What's also surprising about these circuits that was, I think, less expected until people started actually measuring them, is that the noise is surprisingly not bad. Especially true if you're using those non-overlapping multi-phase LOs with at least 4 phases, perhaps more. And this allows for well-documented noise figures of 3 dB or less in the core mixer itself. So this is a very exciting capability. You have something that can act as a filter. It has great out-of-band linearity. It has a decent in-band noise, and so it's really kind of caught on as a technique that gets used in a lot of places. So what can it accomplish? Even 10 years ago, when we first started looking into space, we saw some interesting capabilities. It gave us the ability to essentially tune the input impedance using baseband components. That's what the plot on the left shows, and to have that match track our local oscillator across more than a decade of frequency. It also we were able to show that it gives good noise figure on the order of 3 dB. And then finally, that it had this very good out-of-band linearity. So back in 10 years ago, we were seeing out-of-band linearities, IP3s in excess of 25 dBm, and associated very good out-of-band compression. And actually, recent work that I'll reference later has actually further improved this significantly. So we're seeing results with IP3s in excess of 40 dBm. So here's what I'll talk about today. I'll do a sort of a review of the N-path concept in a little more depth. I'll talk about a bunch of the applications it's seeing. Then I'll talk a bit about sort of the limitations on this. When you have a new circuit topology, and this is in many ways a new circuit topology, you need a sort of a theoretical framework to think about that. So I'll talk about that and some of the ways that those insights are useful. Then I'll probably take a break, and then I'll talk about the implications of this theory and these circuits when you go to higher frequency, when you move from sort of the single gigahertz regime to higher than that, what limits you, and then some of the work we've been doing to try to overcome that. Okay, so just to understand how kind of conceptually how these things work, the basic setup, we have our 4 switches. They're driven by our 4 non-overlapping pulses. We have an RF port that we're looking on the input. We have 4 outputs that are essentially phase shifted by 90 degrees, and so therefore give us a differential IQ output. And so that's basically a mixer. It's a classic down conversion mixer on your first glance. So now if we look at that mixer, and we inject a RF current at a frequency close to the mixing frequency, essentially gets downsampled, and so we now see that current gets split up into 4 distinct paths, where as the local oscillator cycles, it samples that incoming current onto the 4 distinct output paths, and that just happens repeatedly. However, because we always usually put some capacitance on the output, essentially that current is going to be immediately smoothed out by that low pass property of the capacitor, and so that what we really see on the baseband is sort of the average current flowing out of the mixer. Then we present some sort of baseband impedance there beyond just that capacitance, and that current is now converted to a voltage that's both proportional to the original sample current, but also to that impedance. And now the critical property of this mixer comes up, which is that it samples both ways. It both was essentially sampling the current down, but also sampling the voltage back up again. And so now if we look just sort of simultaneously to that down converting current, we now see a re-up conversion of the voltage into a stair-step waveform that closely matches the original incoming current. And these samples are inherently concatenated on the RF port. And so now what we see is an incoming sinusoidal current and a re-up converted voltage that's sort of tracking it. Now, one important thing to remember when we think about these things is sort of some mixer basics. If we have quadrature down conversion, we bring in an RF signal with an amplitude and phase. It gets downsampled to quadrature, which has in it both the amplitude and phase information, but usually some gain as well on top of it. And if we follow that by a correlated re-up conversion, what we get back is the original signal we put in just modified in amplitude. The original phase information and amplitude information, our phase and magnitude information are still there, just multiplied by some additional amplitude term. So what that says in terms of our sort of high-level intuition for the passive N-path mixer is that the input voltage now can be described as just the input current times some impedance. And furthermore, that input impedance depends on the baseband impedance. And so we're seeing now that the RF voltage preserves the magnitude and phase information of the RF current, but now multiplied by a constant that is based on the baseband impedance. So why is that cool? Well, if we present the baseband with a low-pass filter, now signals that are downconverted near DC see a finite large impedance, and signals that are downconverted well away from DC see a low impedance, and so are suppressed. And that effect also shows up on the RF port input, just upconverted around the local oscillator. And so now we see an impedance that looks bandpass filter based solely on the local oscillator frequency and on the baseband impedance properties. Okay, so that's you can sort of see why that's a neat capability. I can now build essentially arbitrarily high Q filters with arbitrary control of the bandwidth and center frequency just set by baseband components in my local oscillator. So what does that get used for? So the first place this has been really broadly seen, and I suspect many of you have already seen this used this way, is in the context of a downconversion receiver, after an RF LNTA. And here the key idea is that bandpass filtering is presented to the output of the LNTA and therefore protects the output of the LNTA from large out-of-band signals and improves your linearity significantly. Also turns out you can do the same thing without the LNTA. This gives you the better linearity still because you have essentially no gain before your mixer, and also the ability to actually control the input port impedance presented to your RF port, which is a nice capability in some cases because it gives you essentially the ability to match on the fly using baseband control. We've also seen versions where there's actually feedback involved, and so you actually use the mixers around an amplifier, and this gives another degree of control with better noise. And of course, they've also been anywhere where you use mixers for receivers, they can also be used for transmitters. And in this context, they're useful from the perspective of giving good out-of-band noise because of the low impedance presented. So that's basic up and down conversion. However, these same exact circuits can be used in other ways. So one way they've been proposed to be used is essentially a shunt filter, where that bandpass impedance is just put in shunt with your receive path and gives you essentially a front-end roofing filter. You can also be used as degeneration. Now what we do is we essentially put that bandpass impedance in the degeneration path of an amplifier. That means the impedance seen is a bandpass filter, but that essentially creates a notch in the gain of the amplifier and therefore suppresses signal and noise in that very controllable frequency and bandwidth. It gives you essentially the ability to notch out one signal in your amplifier. You can also incorporate them into more complicated filters, and so sort of LC networks to give you higher Q. And finally, they've been shown to work well as series notch filters, where you just basically change your topology a little bit, and now you get a notch instead of a bandpass filter. But it turns out you can even go beyond that. You can use these to do other kinds of selectivity. So Harish Krishnaswamy's group at Columbia showed, in the last 5 so years, that you can use these same structures now to do selectivity in terms of direction of propagation around a loop. So you can use it as a form of circulator. And in this case, it suppresses the signal going one way and passes it in the other, but it's still the same underlying structure with the same sort of properties. And also, it's been shown to be useful in beamforming contexts in a MISO system where you the filtering in space you get from combining the outputs of a set of these mixers translates to filtering in space on the RF inputs, so that an out-of-beam signal coming in is suppressed right on the input, right at the antenna, rather than having to pass through a set of circuitry before that. So the takeaway is that this basic structure shows up now in a lot of different places and is useful for a lot of different things. And so it's really worth understanding well. So with that, I will talk a bit about a lot of the work we've done on sort of the fundamental limits of these things, sort of understanding what they're capable of, because of course they sound great, but nothing's ever perfect, nothing's free. So understanding what sort of bounds them is useful. And also that helps you with the designs. And then I'll show a few of ways that these insights have been used already to make for better systems. And then I think we'll take a break there before I go into the higher frequency side of things. So just to get a little more depth in our understanding of these mixers, we'll look at the 4-phase version of this N-path passive mixer. And 4-phase mostly because it's the most commonly used one, because it gives you basic quadrature. So the mixer samples basically 4 windows, each of a width, T/4, so 25% duty cycle. That inherently has some loss associated with it, because that sampling is not perfect sampling, and so there's a sync function hiding in there, and that gives you a loss of about 0.9, it turns out. Now you can show, and I will show a little bit about this in a minute, that this is exactly equivalent to, can be modeled as basically just having two resistors in your system. The first resistor is the series resistance of your switches, because they're never perfect, they have an on resistance. And the second resistor is this shunting resistance that comes after that. And that shunting resistance basically captures the sampling loss we're talking about. So you can compute out what that shunting resistor needs to be to make the math work out, and it's what I'm showing down here. It's basically just the combined impedance of the source and switch, then multiplied by this function of a sinc function, just as we saw here. Now, so one way you can interpret this is just as a purely as a sort of a sampling phenomenon. The other way you can interpret it is saying that shunting resistance we saw is actually represents a form of loss, right? Resistors are a way you lose power, and that R shunt needs to somehow capture loss of power. And what we can see is that where it comes from is the fact that when we down convert the sine wave and then re-up convert again, they're not perfectly matched, right? There's a difference between, let's see, I'm not sure oops, that's all right. The difference between the sinusoidal waveform and the sort of stair-step waveform you re-up convert. And if you look at that difference, which I'm showing the bottom left there, you can see what's left is a bunch of sort of higher frequency harmonic content. And so if you actually measure, and we've done this, the RF port of one of these mixers, what you'll see is that you put in the signal you wanted, and then you get back that signal's reflected by the impedance of the circuit, but also you see reflections at odd harmonic sidebands. And so if you actually sum up those odd harmonic sidebands, just the power lost to the re-radiation of those sidebands, you get back exactly the number we predicted from sampling theory. So one way of interpreting that R shunt is it's just represents the shunting loss of power that's down converted and then re-up converted to a different sideband, and therefore leaks away into the source. So now if we sort of combine this together, we can say we now have a model so far of the impedance that this mixer presents in terms of its series switch resistance and this shunting harmonic loss. Now, if we include an actual baseband impedance, like explicitly, the way we can think about this is we can say, as kind of I mentioned before, we have an incoming RF voltage. It's converted to a current by just the series resistance of the source and the switch. Once it's down converted as a current to baseband, it encounters the baseband impedance, which creates a set of baseband voltages, and then that's essentially re-up converted and fed back. And so you can analyze this as essentially a feedback problem where the baseband impedance is in the feedback loop. And each of these down and up conversions comes with, again, with that same sampling loss function, that sinc function. So then you can, if you look at what the baseband impedance is, if it's a simple RC, as I'm showing here, you can compute it. It's just basic math. But then when it's up converted, it's then modified by essentially a sampling factor, which you can compute from the sinc function. And for the 4-phase case, it ends up being 2 over pi squared. And so I can just include that in my model. I say now, looking into this, I see the source impedance, I see the series switch resistance, the shunting loss from harmonic re-up conversion, and then this scaled version of the baseband impedance, which I can control however I want. And so that's what lets us do now. So one of the neat capabilities of N-path mixers is they give us the ability to control the RF impedance using baseband components. And so how do I implement that? It's just a combination of tunable capacitors and tunable resistance. And if I want my resistance to be low, I probably will implement it in a feedback mechanism around an amplifier. And now I have the ability to essentially entirely tune the bandwidth and magnitude of that resistance. However, from our initial modeling, you can see that the range of impedances we can hit is bounded. We can't make an input impedance that's less than the switch resistance, because that's always in series with our baseband impedance. And we can't make an input impedance that's more than that shunting resistance, that harmonic loss resistance, because it's in shunt with the baseband. And so we can see sort of on the bottom right here, there are upper and lower bounds on the impedances I can hit. And actually, as I'll show in a minute, you can not only generate real impedances this way, you can generate complex impedances of arbitrary choice, and these same bounds still apply. And so the way you can look at it is the input achievable impedance range. It kind of looks like a Smith chart, but it's not. This is just the input resistance and reactance plotted, and you can see that essentially forms a circle that's bounded at the low end by the switch resistance and the upper end by the shunting impedance. So if my goal is to build a good filter with a high rejection ratio from in-band out of band, then I really need to care about these two limitations: the upper bound set by R shunt, the harmonic loss, and the lower band set by the switch resistance. Now, just a little brief side point. I mentioned that you can do complex impedance, and one way to achieve that is basically provides some path where current on the I path generates voltage in the Q path and vice versa. And so as an example of that, we showed already how to do a resistive impedance just in feedback around an amplifier. If we provide cross connections between I and Q appropriately, we can then generate this cross coupling, and that generates a complex impedance. And now we have the ability to generate, a full set of complex input impedances just based on baseband components. And we can switch the polarity by just switching how those resistors are hooked up. Now, another thing that people have looked at a lot in the last few years is how to enhance the filtering. So if we just have a simple RC, then that's basically a one-pole roll-off at baseband, and you can show that translates when you upconvert to the RF port to just a classic single resonance. So it looks a lot like an LC resonance with a center frequency at your RF frequency and a Q that's just set by your bandwidth. And so that gives us sort of basically a limitation on a relationship between your bandwidth and your transition band, which is typically about a factor of 10. So if I really want to suppress an out-of-band signal, I need to get about a factor of 10 out relative to my bandwidth before I have it fully suppressed. I should also point out here that there's a sort of a lower bound that we care about, at least from the input impedance, which is that switch resistance, which sets the lower bound of input resistance. So once our baseband impedance drops below a certain point, it no longer really affects the input impedance because we're now bounded just by the mixer itself. Now, if we have a sharper, faster roll-off, that would be great, right? So can we build something that gives us a higher order baseband impedance roll-off, which then translates to a higher order RF filter? And indeed, as I'll show, we can. And this, if we even just do a second order one done correctly, that dramatically reduces the transition band and lets us put like pretty much fully suppress signals that are only sort of one full bandwidth separated from your operating bandwidth. It gives you a much more general purpose sort of filtering property. So there's been a couple ways proposed to do this. One was proposed both by my group and shortly before my group, unfortunately for me, by Eric Klumperink and Bram Nauta's groups. And that's just basically to include a little bit more feedback in your baseband, where you put some positive feedback on some feedback capacitors. And that, very much like a Salon key filter, generates a higher order response, both in the sense of giving you 40 dB per decade roll-off, but also a little bit of peaking at your band edge. And the only real limitation here is that you need to include some, so that gives you the 40 dB and the peaking. And the only real limitation of that positive feedback capacitor trick is you need to, it can go unstable on you. So you need to include some series resistance, which adds a 0, which basically means you only get that sort of 40 dB per decade roll off over a relatively narrow frequency range. Usually about a factor of 4 in frequency is what gives us a good stability. But that's actually quite a lot of roll off, and enough typically to get you down to the sort of floor set by your mixer. So this technique has definitely worked. And it gives you that, again, that sort of transition band to bandwidth ratio that's only a little over 1. The one downside of this approach is it does mean you need to worry about the noise and linearity of your baseband itself, because you are putting in positive feedback, which means it's actually being amplified at that band edge, and you have to like basically burn more power in the baseband to compensate for that. A second approach that's been looked at is to, instead of putting in just an explicit second pole, you actually put in a notch, and this can be now a completely separate shunt function. And the structure that works for this is shown on the left here. It's basically effectively all AC coupled, but has an active circuit that generates that notching function just out of band. Interestingly, it also consequently generates a second pole and actually a complex pair of poles. And so you can still get that sort of band edge peaking, but now you also get those complex zeros giving you a notch. This actually gives you an even better transition band to bandwidth ratio. So you can even, you roll off even faster. It's about 0.9 in this case. The only concern here is that beyond a certain point, the filter flattens off, and so you need to make sure that flat zone is at least below the on resistance of your switches to get the best rejection you can. So this is actually, there's been a number of groups getting into the space lately, and so this is just sort of a sampling of what's possible. But it's definitely the case that you can do better than a simple RC roll off on the output of your mixer and get a better filter. Now, sort of stepping back now, I've talked about sort of a simple model for the the impedance we see here, the series resistance and the shunt resistance that are inherent to the mixer, and then this controllable baseband impedance that gives us the filtering and everything else we want. Now, one of the reasons we care about this is that loss in an RF system is directly upfront, right? It's directly related to noise figure. And we have two loss mechanisms. The first is just the series resistance of the mixer, and it will increase your noise factor essentially by a term proportional to the ratio of those two resistors, which says you want the switch resistance to be small to improve your noise factor. The second is that due to that loss due to the sampling or harmonic radiation. And that is degraded by a factor related to both the shunting impedance and also the switch and RS. And so the overall noise factor includes both, and means we want to minimize our switch, but also maximize our shunt. And the question then is, how do we actually maximize that R shunt? Like, what can we do for that? And it turns out the answer is to add more phases. And so early on, people, including us, got interested in more than 4 phases for harmonic rejection. And the way to make that work is you actually have to have still non-overlapping pulses. So now instead of 25% duty cycle pulses, you have 12.5% duty cycle pulses. And then you can follow this up with harmonic recombination, either in analog circuits or in DSP afterwards. And that gives you the sort of the classic benefits that Weldon showed 20 years ago of giving you harmonic rejection in the down-converted artifacts. However, it also has interesting effects on the core loss parameters. So now we're using 8 phases instead of 4 with these sort of narrower pulses. If we recompute our basic sampling function, we find that it's a slightly larger number than before. Before it was 0.9, now it's more like 0.98. But more critically, when we do that down and re-up conversion, the re-up converted waveform is a lot closer to a sine wave. It's much cleaner. And that means the sort of residual things that are not being matched are smaller, and particularly they're at different harmonics. And so in fact, it turns out if I do a down and re-up conversion using an 8-phase system, I get a natural 3rd and 5th harmonic suppression on my RF port, and therefore a reduction in the amount of loss I have, because there's much less harmonic content being re-radiated and sort of dissipated into the input. And that means that the shunting impedance is now about 4.5 times larger than it was for the 4-phase case, which means I have a wider impedance matching range, and as I'll show here. So if you look here, I'm just comparing, it's basically the same circuit just in 2 modes, either a 4-phase or an 8-phase mode, initially with a very low baseband impedance, so the input impedance is low, it's under 50 ohms. As I increase that baseband impedance, I can see that I'm beginning to get that bandpass filter property I expected, but we'll notice that the 8-phase one is already larger than the 4-phase one. And that becomes, especially as we maximize the baseband impedance, we see that the maximum impedance the 8-phase hits is significantly larger than the 4-phase, and that's because that shunting impedance is a significantly larger number. Now, a little aside, that if you play around with these circuits for a while, okay, so those are the numbers for how much better it is, sorry. Now, a little aside, if you play around with these circuits for a while, you'll find that what almost always happens is that peak, which was supposed to be centered on your RF frequency, is actually offset a little bit. So it's a little bit asymmetric. You'll see that the peak is offset. You'll also see that the sort of tails on either side aren't quite symmetric. So that's a little bit weird, and it has caused a lot of people over the years to sort of scratch their heads. So we can discuss that just briefly. So why do we get this asymmetric effect from the capacitive roll-off of our baseband when it's re-up converted to the RF port? And the way you can understand that is by looking at the actual impedance that RC is presenting. It has a real component that looks very low pass. It also has an imaginary component that starts out at 0, goes up to a finite value, and then decays away again. And that's just inherent to a parallel RC. However, when it's up converted, right, it's up converted around the local oscillator frequency, but it turns out that actually the lower sideband is the complex conjugate of the upper sideband. And so what I see in terms of impedance is a bandpass real impedance, but actually this asymmetric imaginary impedance. And this is entirely predicted by the math. So if I actually look at the predicted impedance presented by the capacitor to the RF port, it's now inversely proportional to the actual value of the frequency you're operating versus the local oscillator frequency, which means that when I'm above it, I get a positive number. When I'm below the LO, I get a negative number. Now, this alone doesn't explain the asymmetry, but now if I recognize that my input impedance also includes some parasitics that typically make it not perfectly real, then we see that actually the imaginary impedance, the real and imaginary impedances sort of match up best, not at the center frequency, but a little bit offset. So I get my match a little bit offset, which means I get my peak a little offset. And all those asymmetries are really just the interaction of the upconverted baseband impedance and its complex conjugate interacting with any parasitics on the RF port. Okay, now let's go back to this sort of core observation that having more phases gives us a larger in-band impedance, and just ask how that generalizes. So instead of having just 4 or 8 phases, if we just have n phases, whatever that number is, we can still predict what that means in terms of gain and loss and so forth. And we see that the gain just goes as the sinc of pi over n. The scaling factor on our baseband goes as the sinc of pi over, again, pi over n effectively. And that in turn affects the R shunt impedance, is this same sinc function. And what we see is that as we increase n, our gain converges towards 1. We start converging towards perfect sampling. The conversion factor from baseband impedance to RF impedance just goes as 1 over the number of phases, n. And that kind of makes sense. It's just like you have n parallel basebands, and they're acting in parallel, so you get a 1 over n factor. And then that KNO, which is essentially the multiplier that gives you that shunting impedance on your original input impedance, goes as n squared. And so you get a significant benefit as you increase n, which helps explain why the 8-phase case tends to be much better than the 4-phase case. Now, we said early on that the primary reason we care about loss is for noise figure. And we said before that we have 2 primary loss mechanisms. We have the switch to the switch to source impedance ratio, which I'm now going to call a dimensionless number rho, because it turns out that's the number that really matters. It's not the actual value of R switch or the actual value of RS, but the ratio that always seems to matter. And the second thing was, again, that harmonic loss term we talked about before, which we now see is, again, related to just basic sinc functions. And so we can compute out what that factor turns out to be, and it's just proportional to the sinc, the 1 over the sinc squared of pi over n. So then from that we can compute our noise factor, and it's just 1 plus rho over that sinc squared term, which tells us that if we want to improve our noise, we have to do 2 things. We have to minimize rho, so that makes the switch resistance very small, and we have to maximize n. And so if we just compute this out for a few things, if we look at n equal to 4, if we allow for a really small rho, so a really low resistance transistor, then the math tells you that the minimum noise figure you can achieve is 0.9 dB. And if you go to 8 phases, that same math says it's 0.2 dB. Now, of course, we're not actually going to build passive mixers that have that low a noise figure, but it tells you that the sort of fundamental bounds here are in fact quite low and not especially limiting. It's more how well you design it and how good your process is, not whether the circuit fundamentally can get you a good noise. And it's also worth noting that these numbers are precisely equivalent to what you get from down-converting just the noise at the harmonics. So that is to say, if we were to compute the noise generated, we can look at it as noise due to the loss from the series resistance and the shunt resistance, or we can think of the shunt resistance noise as actually just being due to down conversion of noise at harmonics. And if we compute the sum, we actually find those 2 numbers exactly converge. And so what I'm showing the bottom right here is the math you get from doing that summation, and then the simulation you get, and they exactly match up. And the only restriction on this is that if you're using more than 4 phases, you need to use a harmonic rejection baseband in order to actually take advantage of it. Now, this also is important because if you're preceding this circuit with an LNTA, then you have to worry about its harmonic noise also, which is, of course, always been true for mixers. And so it isn't changed here either. It's an ongoing property of these mixers, just like all the others. Now, I want to talk a little bit about how we think about linearity in these circuits, because that's actually the big win. And so why is linearity so useful in these n-path passive mixers? So we know we have a low-pass filter on the baseband, and so that's going to essentially protect any circuitry from out-of-band signals after the mixer. And we also know that that impedance is actually upconverted to the input of the mixer, which should therefore also protect the input to some extent. And so we expect that for out-of-band interferers, the properties of the mixer should essentially work to, in effect, sort of suppress the effects of out-of-band interference and make for a more linear circuit. And actually, it turns out this is true in more than one way, as we'll see now. So just to see how you can think about this, you can basically, what we'll basically do is we'll look at one MOSFET, we'll ask how it behaves, and particularly we'll ask how it behaves out of band. Out of band, the shunting capacitance on the baseband basically shorts you to ground. And we can just basically look at the current or the distortion in the drain current as a function of the incoming signal. And then we know that once we've done that, which we can compute here. Actually, I should say once we've computed that current, then we can just assume it's being down converted to get the baseband distortion products. So we're just going to do a third order Taylor series analysis in terms of the VDS of the transistor. And to model that, what we need to include is both the sort of core square law behavior of the trioded device, but also velocity saturation, because we're typically driving these transistors pretty hard. They're typically in a place where a dominant nonlinear problem is velocity saturation. And to model that, I should note that we're using a slightly different model here than the sort of the standard one you see, where we're actually using a square root and squared function rather than the sort of absolute value you see in a lot of other cases. And that's because it turns out if you use the more traditional model, it actually has a discontinuity at VDS equal to 0 and basically breaks all of your math. And this one I'm using is actually a more accurate description. So just to sort of see where the various distortion terms come from, you have your switch resistance, which is just 1 over GDS. The second order nonlinearity comes primarily due to set by the overdrive voltage, so how strongly your gate is driven relative to your source and drain. And your third order nonlinearity predominantly comes from the velocity saturation effects. So how much velocity saturation you see in your channel as you increase VDS. And then, as I said before, once we have these distortion terms, the switching phenomenon of the mixer basically downconverts whatever distortion terms are generated. Now, a neat effect here, though, is that we're typically designing a case where the on resistance of the switch is actually less than the source impedance. And that source impedance now actually acts a bit like a degeneration and reduces the distortion. And so I'm not going to do the details of the math, but you can just do sort of standard feedback or degeneration math on this to see what the new nonlinear terms are. And what you see, most importantly, is there's a strong dependency on that term rho, on that ratio of the switch resistance to the source impedance. So for example, if I compute IP3, I find that it depends on both my overdrive voltage and my velocity saturation, but also depends strongly on rho. And as rho gets small, my IP3 gets quite large. And so the key point is, if I want to be very linear, I want to minimize that ratio, that R switch to RS ratio. I also would like to maximize both my overdrive and my velocity saturation, but these are typically bounded by my process, like by my transistors and by how hard I can swing my gates before something breaks down. So this math does a pretty good job of predicting measurement. So if you put in reasonable numbers for a CMOS process, and then you measure the IP3, the numbers predict IP3s in the 20s of dBm, like 25, and the actual measurements are also on the order of 25 dBm. And so everything matches up pretty well. It also suggests that if you can get a better transistor from a linearity perspective, you can get a better performance. And so we've actually done this in collaboration with some colleagues of ours at Raytheon. We built a system where the core mixer was actually built out of gallium arsenide rather than silicon, but with LO and baseband circuits in silicon. And what we note is that we compared that design to an otherwise equivalent CMOS design. So the switch resistances are the same in between the two mixers. It's just the different technology. The consequence is the noise figure over most of our frequency range matches up. It's a little high in this case, but it's high in the same way, so it's at least consistent. But we see that the gallium arsenide provides about 10 dB improvement in our compression point, essentially, our out-of-band compression point. And that's directly related to the fact that we can both drive the gates of the gallium arsenide transistors harder by about a factor of 2, and also that they have typically better velocity saturation properties. And so if you want to get a better sort of linearity property for the otherwise same noise and loss parameters, you basically have to move to a better transistor. That's the solution. So now if I just sort of summarize my analysis at low frequency, there are two design parameters we have. We have the switch to source impedance ratio, and we have the number of phases we can use. And that directly impacts both the input impedance that you can see, which you can control with your baseband, but more importantly, the range of input impedances you can see, which are limited by by rho essentially, and then by the number of phases that sets your R shunt. And if I want to improve that range, then I want to reduce my rho and increase my number of phases. So the noise factor turns out has exactly the same dependencies. And so one way of looking at this is even if you don't care that much about your impedance tuning range, you still actually care because your impedance tuning range directly matches up to your noise factor. So anything that you do to improve your tuning range also improves your noise factor. And then finally, out-of-band linearity depends on some sort of process-dependent parameters that give you your distortion, but also which are unfortunately limited by things like gate breakdown, but also are strongly dependent on that term rho. And so at lower frequencies, at least, there's a consistent goal of trying to make your switch resistance as small as possible relative to your source impedance. So one interesting side effect of this is usually the way people view this is, oh, I need a smaller switch resistance, I'll make my transistors bigger. And then I run into, which makes my noise figure better, it makes my linearity better, but does cost me significant power to drive them. But the other way to do it is to actually deliberately increase the source impedance by, for example, putting in a transformer between your source and your mixer. And this, or some other form of impedance upmatch. And of course, the one thing is, because we're worried about harmonic effects, that impedance upmatch works better if it's a relatively wide band match. So a sort of a narrow band resonant match doesn't help you as much. But if you do that, what you see is that of course your noise figure gets better, but actually your linearity gets better, even though your input signal got bigger too, because the sort of the net effect is a benefit. And at the same time, you can save significant. Say this. You can also save significant power because you are now allowed to use much smaller switches. And I should note that one of the ways this gets used is to actually do two things at once: to both upmatch your impedance with a transformer, but also use it as a balun to go into a double balance mixer. And so you'll see a number of designs that are now sort of using this fact that I want to minimize rho, and I can do it more than one way, and I should do them all. This also directly impacts how I co-design with an LNTA, because now what I want to do is present a reasonably high output impedance on the LNTA, because that's what the mixer wants to see. And when I do that, I also naturally protect the output of the LNTA, because it sees a high impedance and therefore real gain in band, but then a suppressed gain out of band, which protects it from those out of band interferers. All right, I think this is a good point to stop and take a quick break and ask if anybody has any questions.
Okay, yeah. Thanks, Professor Molnar, for this talk. Actually, yeah, maybe at the very end, when you have a transformer up conversion, you mentioned that it should be wideband.
Yes.
At like transformation. Why is that, and what happens if it is kind of narrow band in the band that we are interested in, let's say like GSM or something like this?
Yeah, that's a good question. So it kind of depends on how it's not wideband, if it's not wideband. So the reason you would want it to be, and I'll talk a bit more about this in the next section, but from a linearity perspective, it probably doesn't matter that it be wideband. From a noise perspective, the thing to remember is that, let me go back a few slides, that the what's the best way to do this? I just need to point out a model. Nope, get out of linearity, go to noise. The kind of the key thing here is that this part of our loss comes from that shunting impedance, and that shunting impedance is actually the sum of noise and loss across a lot of harmonics. So if we do an impedance up match, but the impedance is only high in band, but actually looks very low out of band, then the harmonic loss will be higher, and you'll actually get more loss there, and your noise figure will be degraded.
I see.
And it's a little
Okay.
subtle, because you could be narrow band for your signal, but just high impedance out of band, and then you'd be fine. But if you show a low impedance out of band, then then your noise figure gets worse.
Oh, I see. Okay, so it's kind of I would say harmonic tuning.
Exactly.
To like, okay, I see. Okay.
Yeah, so that's right. If you were to put in something, sorry, I'm moving back to where I was before. If you were to put in a structure that presented high impedance at the third and the fifth harmonic, for example, even if it was narrow band high impedance, that would still be beneficial.
I see. Okay.
I got a question here,
Yeah.
Professor. So, what's the relationship between the RC time constant versus the sampling clock frequency in order for this?
That's a good question. And so, actually, in the stuff I've shown so far, I'm making one critical assumption, which is that the RC time constant is a lot longer than the sampling frequency, like a factor of 10 or more. If you move away from that so that your output bandwidth is on the same scale as your sampling frequency, like within a factor of 10, say, then a lot of this math breaks down, and mostly it makes things worse. It makes essentially the system tends to benefit from some memory from cycle to cycle, and if you start to lose that, it works less well. People recently have been looking at designs, including us actually, where we put a a bandpass filter on the output rather than a low-pass filter, and that can work. You can do IF systems that way, but the restriction seems to be that the bandpass filter's bandwidth still be narrow relative to the RF, like the clocking, the LO frequency. So the kind of key thing is that you have memory from cycle to cycle. So that can be a low-pass memory, or it could be a resonant bandpass memory, but that seems to be really important.
Thanks.
And yeah, maybe also is that like your edges were sharp in the model that you were deriving once it have slow rate.
Yes,
It will be having.
that's in the next section, so I'll talk about
Oh,
that.
I see. Okay, good. Okay. I think we have a question. Thanks for the presentation. Sometimes people use an inductive load at LNA output side or mixer input. Does it mean the transfer function becomes RLC and getting better selectivity?
So what you find is if you put the appropriate inductive load at the input of the mixer, it gives you an additional layer of selectivity. What usually is true is that if the mixer's baseband is reasonably narrow band, it will dominate. And so what you'll sort of have is in band, you'll have a sort of narrow band bandwidth set by your mixer, and then you go out sort of flat for a while, and then at some point the sort of roll off from the LC resonance kicks in, and your impedance drops even further. But actually, maybe a more useful reason for putting that inductor in there from the perspective of what we talked about here, let's see if I can get back there, comes from, and I'll talk a bit about this more in the next slides, but I was talking about that sort of asymmetry that you see sometimes. I'm afraid I'm going to have to go back too far here, but here, right? So we're talking about this asymmetry here. One way that having a resonance out front can help you is it can actually make sure that the RF impedance the mixer is seeing is purely real and not imaginary. And when you do that, that actually will cause this peaking to center up. So you actually get a slightly different interaction than you might expect, where the LC filter doesn't set your bandwidth, but does set your center frequency by guaranteeing that your mixer center frequency is actually centered up at the LO and not offset by the sort of interaction you see otherwise. So getting it, making the input impedance look real is actually maybe more important than the actual resonant like bandwidth effects of an inductor.
Okay. And what is the effect of the number of phases on this offset?
That's a good question. It's not. It depends. If you don't have overlap, which
Yeah.
I will talk about, then it's not a huge effect, except that it can allow for a higher Q filter effect effectively, because it raises the upper bound on the in-band impedance, and then that will then have an interaction. So if it's higher Q, then it essentially will shift more for the same amount of parasitic, or it'll appear to shift more. But it doesn't have I haven't at least seen a super strong effect of having more phases. It's not not the dominant thing. With actually, now I think about one caveat, which is that as you go to more phases, there are fewer harmonics involved, right? Because you're suppressing them, and those harmonics can also interact with your front end resonance and shift you around a little bit. So you get a little better control over the effect of the harmonics if you have more phases, which can make things a little bit more predictable.
See, okay. I think
Get back to where I was
have
here.
Yeah, I have one last question.
Sure.
For the R switch R shunt model,
Yes.
it is like, as I see that it is like it is doing at RF. It
Yep.
is like basically. So how can we get? Does this model also predict the baseband signal?
It does. It's the key difference is if you look in from the baseband, so it predicts the impedance you see looking in from the RF. It does a reasonable job predicting what you'll see on the baseband as well, except that there's sort of a modifier on there, which is that the baseband signal has essentially a gain attached to it, so associated with the sampling waveform. So all the numbers shift a little bit by that sync of pi over n, but they sort of track each other, if that makes sense.
In terms of magnitude and phase, like,
Yes.
is there any delay that is being introduced with the system? Assuming that we have very sharp edges and like.
Right. There's not really delay because the behavior you see on the RF port is essentially a closed loop behavior. There's essentially feedback going on between the baseband and the RF port. So they're both the baseband and the RF port are caught in that feedback behavior. The feedback is just through the resistances, but it's there. And so they're reasonably well synchronized. You don't see like a phase shift delay per se. What you can see, sometimes you'll see things that look kind of like that, but you can also explain that as just that same interaction between a non-real input impedance. If your input impedance is complex, then we get that sort of shifting of the peak we saw before, and that looks like that manifests as something like a phase rotation on the baseband output. Those are related to each other.
I see. Okay. One question we have, it seems the N-pass mixer works well with voltage mode mixers due to the voltage built up at the baseband side. Can you please share your view if this also works with current mode mixer, where the baseband side is, for example, an AC ground due to TIA usage?
So what I've seen is that if you put it in the current mode, in some ways it's better because you get the great linearity everywhere, because essentially it's always looking at at least ideally, it's always looking at a low impedance on the baseband port. The kind of the downside of that is that you have to have a significantly better baseband amplifier, because it has to actually maintain that low impedance on the input the whole time. And actually, the place that usually becomes a real problem isn't really in band, because in band you just have a lot of gain, you're great. And it's not way out of band, because way out of band you have a capacitor shunting you, but sort of middle out of band, sort of in the band edge. When your amplifier starts to lose gain, then the input impedance stops looking like an AC ground. And then you get the worst sort of linearity effects in sort of the transition band, because you no longer have a good AC ground from active feedback, but you don't yet have good AC ground from a shunt capacitor. And that's kind of where the trouble tends to arise. So I don't have the best answer for that, but that's sort of the simple version. Now, what I will say that we've seen is that all the loss mechanisms I've described with our shunt and stuff, that actually is entirely still true for the current mode. So even if I set the output to look like an AC ground, that shunting loss is still there, and it actually still effectively generates noise and degrades your performance. So that model is completely general, regardless of what you do on the baseband.
Yeah. Okay. Thank you, Doctor, very much. With that, I think we can continue.
Okay. So some of those questions were good. They sort of are a good segue into the next piece, is to kind of ask what happens as we go to higher frequencies. Because so far I've been making some sort of assumptions about that. So it turns out when you go to higher frequencies, there are two primary things that limit you. One of them is just parasitic capacitance on your RF port, and the other is what Muhammad was asking about, which is that your edges are no longer super sharp, and so I start getting overlap between my LO signals, and that's a new form of loss that I have to worry about. So I'll talk a bit about both of these and some of the ways and then actually a lot of our recent research has been on mitigating them, so I'll talk about that as well. Okay, so to sort of set this off, it's good to just have a little bit of a sense of kind of what our limitations are. So if we think about that input capacitance, right, even if we do everything else well, we're always going to bring in parasitics from the mixer itself. And that parasitic capacitance is going to be proportional to the width of the mixer. Whereas the switch resistance, the on resistance, is inversely proportional to the width of the mixer. And so I can actually define an omega M, we'll call it, very, very analogous to the omega T of a transistor and an amplifier. That's just 1 over the product of those two terms, and it's independent of the sizing of the device. We still have that term rho, which is the ratio of the switch resistance to its source. And so now we can say it's basically omega M is set by our process and also by the number of phases in our mixer, but not by the sizing of the devices. And so we basically choose the sizing based on our choice of rho, and then omega M just comes along. Now, why do we care? So we can note that if once we have that capacitance in there, which of course we do, we'll have essentially a low pass behavior on the input. We'll have a shunting loss that will directly affect our signal and essentially affect our gain. And so now what we see is an input impedance that is basically okay. But then, so we have the shunting capacitor. We can turn it around and also say what impedance do we see looking sort of back from the baseband up converting, and we'll see that same sort of low pass behavior, but flattening off at some lower level where the switch resistance starts to dominate, sort of in series with that capacitance. Now, this doesn't necessarily matter so much for your signal unless you get to really high frequencies, because that omega M term is typically in the same ballpark as the omega T of your transistor. So in a modern process, it's 100 gigahertz or more. However, the real problem turns out to be, and furthermore, I can resonate it, right? So I can play all of my historical sort of RF games to try to recover signal gain out near where that capacitance starts to dominate. The problem is that the loss mechanisms for these mixers are not just in band, but also all the harmonics. And so even if I play resonant games for my signal, my harmonics don't see that resonance unless I do some very fancy resonant network. And therefore, they still see that reduction in source impedance. And this will directly impact that shunting loss mechanism. So we can just do the math. We can just basically add up. Before I said that the shunting impedance was basically just captured the loss at all the harmonics. For a simple RC case, I can do that same math. I can compute all those losses. I can just make this big giant sum. And I can sort of look at two scenarios. I can look at the low frequency case, where I'm way below that omega m term, below rho omega m even. And down there, I get back the number I had before. This is a reformulation of the term I had before, where that k and o is just that sinc function, and then just r switch times the 1 plus 1 over rho. However, at high frequencies, now those harmonics are going to be shunted by the parasitic capacitance on the input, and so they won't see as much impedance. And therefore, when I do that sum, I'll get a larger number. And if I go to a sufficiently high frequency, what I get is something that's now that same k and o term, but just times r switch rather than times that plus rs, which is about rho times lower. So I get rho times more loss, and my noise figure and everything else will be great. If I want to be a little more detailed, I can actually write out the sum. I can state that my shunting impedance is proportional to my switch resistance, and then some dimensionless function of the frequency ratio of where I'm operating to omega m, my mixer's property, and then rho. And I can write the infinite sum, and it's horrible, and you don't want to solve that. But it turns out if you actually do solve it and do some curve fitting, it's very closely matched by a much simpler function, which I'm showing in the bottom left here. And the critical point of all this is that if I now look at just the ratio of that shunting loss to R switch, I get a curve like I'm showing here, where the x-axis is just normalized frequency, and the y-axis is normalized resistance. And I see once again that having more phases really helps. I get a much larger R shunt, which is good. It's less loss. But those benefits all roll off significantly as I approach omega m, and I get significant roll off when I'm even a factor of 100 below omega m. So this problem kicks in. If my omega m were 200 gigahertz, then this effect would start kicking in at about 2 gigahertz, and I have to worry about it much earlier on. So we can see this both, the math predicts this, but you can see this in simulation as well. So what I'm just showing here is for a generic 65 nanometer process, the computed and the simulated impedance range we can hit on the input for different frequencies. So for a very low frequency at 50 megahertz, right, we have our full range we can hit. We go up to 500 megahertz, we still hit most of that range. When we go up to 5 gigahertz, we'll notice two things are changing. First of all, that reachable impedance range is much smaller, but also you'll notice that the curves are all sort of shifted. And the shifting is due to the imaginary impedance of the capacitor essentially just moving all of my impedances around. Now, you see a capacitor messing you up on your input, the first thing you want to do is add an inductor to try to resonate it out, and you can do that. And you'll notice when I do that, I see that the rotational effects go away. I've basically canceled the in-band effect of that capacitor, but the reachable impedances are still about the same. And that's because the effect on our shunt due to harmonic losses has not been helped by that inductor. It's still just shunting straight through the capacitor. And so as I go to higher frequencies, I just basically can't hit as wide a range of impedances. Now, as I've said several times already now, one of the main reasons to care about those impedance ranges is really because they directly relate to your noise figure. So we can see the same thing for noise figure. At low frequencies, we can compute out what the noise figure, reachable noise figure is. When we go to higher frequencies, we see that the noise, the sort of effective noise from our shunt gets about rho times bigger. And so we see significantly more noise from the harmonics, basically because we're seeing much more loss to that R shunt term because of the parasitic. And once again, we can show the math is that the current we predict from essentially down conversion of resistive noise in the mixer versus the current we predict from that R shunt model end up being current noise, I should say, end up being about the same. So what does this all mean? What this means is, as I go to higher frequencies, I can compute out what my noise factor will be. I still have that 1 plus rho out front, but if I look beyond that, I have a somewhat more complex function of rho and omega due to the R shunting. And it turns out that function is actually non-monotonic. And so if I look down below, these are just some simulations and with the math overlaid. And what we'll see is that as we sweep rho, at low frequencies, as we make rho smaller, the noise figure just gets better. But as I go to higher frequencies, so now 5 or 50 gigahertz, what I see is that that's no longer true. Is that as I make rho smaller, at some point I actually get a worse noise figure, in part because as I make rho smaller, I automatically make the transistors wider and therefore make the parasitic capacitance worse. And so that suggests that at higher frequencies, for optimal noise figure, there's actually some optimal rho that you want to hit, not just making it as small as possible. And then the trade-offs get interesting because for noise, there's an optimal rho, but for linearity, you just still want as small rho as you can get, as wide a transistor as you can get. So you have to sort of balance optimal noise figure against optimal linearity. Whereas before, they had the same, at low frequencies, they have the same requirement. So in summary, if you think about noise here, good noise figure is possible in passive mixers. Theoretically, you can get less than a dB. Many people now have measured less than 3 dB noise figures at 1 gigahertz range. And that noise depends on the relationship between the switch resistance, shunting loss impedances, and the source impedance, where that shunting captures the sort of the harmonic noise down conversion and signal up conversion. And making N bigger does help a lot. So if we just look at sort of the goals, that if you're sufficient low frequency, your goal is just to minimize R switch. You just make your transistors really wide. When you go to high frequencies, it's more complex, and you have to sort of optimize that R switch. And if you look at the fundamental limits, at low frequencies, the 4-phase limit is 0.9 dB, we said. The 8-phase limit is 0.2 dB, which just basically says that the fundamental limit is not what limits you. It's more the implementation. If you go to very high frequencies, as long as you keep your in-band signal happy with resonance, the limits are still not terrible. The fundamental limits are more like 4 and 2 dB, which is somewhat more limiting, but not catastrophic. So this can even work at high frequencies, provided you optimize the switch resistance properly. Now, one thing that I haven't talked about is sort of the intermediate case where your in-band signal is low enough that a few of the harmonics are sort of still, if you will, in-band, below that omega m. And this was a situation that actually Eric Klimperenken and his collaborators worked on some years ago. And what they showed was basically that if you deliberately resonate not for your fundamental frequency, but for harmonics, you can essentially boost the impedance those harmonics see, and consequently reduce the loss you get, and actually beat that fundamental noise figure we said of like 0.9 dB for a 4-phase mixer. So there's still a place for resonance in all this, just that you design it a little differently. You sort of target it more at the harmonics than you do at the fundamental. And then you can get actually a better performance out of it. But this only works at sort of intermediate frequencies. If I get too high frequency, the parasitic capacitance goes back to dominating, and adding inductor doesn't really help. Okay, so that's it for the harmonic loss thing. Let's talk a little bit about overlap, and then I'll talk more about it again. So the other high frequency mechanism you have to worry about is the fact that as I'm switching my switches, they're no longer perfectly non-overlapping because I have sort of finite slew rates on my pulses. And so I'll get these periods periodically where two switches are on at the same time, and I get a loss mechanism where I can basically lose charge from one of my basebands to the next. This, of course, happens at every transition. And so if I can do some bookkeeping on this and just sort of compute how much total leakage I get, and therefore how much total loss I have. And if I do, I can show that it's equivalent to having another one of these shunt resistors. So I had a shunt resistor from harmonic loss. Now I have another shunt resistor due to that overlap effect, where I get leakage from the overlap. And that in turn impacts all of our math a little bit. It impacts the noise factor we can achieve, and thereby impacts the optimal rho that we want to use. And so kind of the takeaway of this is that when you're going to these high frequencies, the fundamental limits from just harmonic loss say one thing, but once you have real LO waveforms, you take another hit on top of that due to their finite roll-off. And what can you do about that? Well, you can burn more power, you just make your edges more steep, but then at some point you run into fundamental limits there. So I'll talk a bunch more about that in a minute. But just to sort of summarize where we are so far, as we go to high frequencies, as we sort of approach that omega m term, or get within maybe a factor of 100 of it, then we have to start worrying about what that term is, what that switch figure of merit is, as well as the switching time of my LO. This starts impacting my impedance a bit. Basically means that my shunting impedances are lower, and therefore my achievable impedance range is more bounded, which in turn impacts my noise factor. And also there's a trade-off there with power consumption, which I didn't really talk about, which basically says if I have more phases, which makes things better, and I have faster transitions, which makes things better, and I make my rho lower, which makes things better, all of those things imply more power consumption. And so, not surprisingly, when I do the things that optimize my performance, I burn more power, and that's kind of hard to avoid. It's also worth noting how this interacts with process scaling. If I go to a finer process node, what I'll typically see is that my omega m gets higher, just like omega t. My transition times get faster, so those both help noise figure at high frequencies, and therefore actually let me do a different trade-off on rho, which improves my linearity. Because if those terms are better, then I can make a wider transistor for the same noise performance and then get a better linearity. But typically, process scaling has made both the overdrive voltage achievable and the VSAT, the velocity saturation, worse. And so as you go to better processes, you can typically go faster, but often with worse linearity. So with all that in mind, now I want to talk about sort of what we've been doing lately to try to really bring these circuits up to the millimeter wave frequencies and even to the high RF. So just this is a slightly out of date chart, but just kind of where things stood a few years ago in terms of the relationship between our sort of effective dynamic range, so the difference between the out of band compression point and in band noise figure relative to frequency. And we see as a clear, not surprising downward trend on that. As we go to higher frequencies, I just can't achieve as high a dynamic range. And so one of our goals has been to try to understand where that trend comes from and see what we can do to improve on it. And one thing we found as we looked into this math a bit more was that if you look at what dominates your performance loss at high frequencies, it turns out that for sort of otherwise things being held constant, it's actually the overlap effects that tend to dominate. So that all that harmonic shunting stuff is fundamental and limits you, but practically speaking, typically the degradation of your LO waveforms limits you more and degrades you more, and also benefits less from having more phases. And so we spent a lot of the last few years focusing more on how do we mitigate the effects of that overlap effect, given that at high frequencies you can't help but have overlapping LO waveforms. What can we do about that? So that's what I'll talk about for the last part of this talk. So the first example of this, I'll talk about ways of mitigating overlap for 4 and 8 phase mixers, and then also talk about ways of generating pulses at very high frequencies. So to just look at the overlap problem, we'll go back to the 8 phase case, because we do know that 8 phase mixers are capable of significantly better performance if you can actually get the LO to work. And we're noting here that we're looking at a 1/8 duty cycle. Now, if we fail on that, if our pulses get wider, which they will as we go to higher frequencies, then I start getting these leakage paths where I get current flowing from one phase to the next, and this will continue as I go through all the phases. And so I see all these sort of leakage paths. Now, if I just rethink my mixer a little bit, just rearrange it so that I have essentially one set of phases above and one set below, so all the 45 degrees phases below, all the 90 degrees phases above, what I'll now observe when I look at those overlaps is that they're always between the two subsets of mixers. So I'm always crossing that middle place, which suggests that there's sort of a path there that if I could suppress current there, I would suppress overlap effects. And so the proposed trick that we've been looking at is just to include a blocker in there. In this case, the blocker is just a pair of inductors. Now, if I do that, now I can get away with actually a worse duty cycle. And in fact, what we did is we built something that instead of being 12% duty cycle, 25% duty cycle LO, but still 8 phase. And that's actually much, much easier to build, it turns out, especially as I go up in frequency. And if I think about how this works, what I can note is that now I have these two 4-phase mixers that are offset from each other by 45 degrees. If I look at the down and re-up converted waveforms, right, I re-up convert the fundamental, but I also re-up convert all those harmonic sidebands. And each of those 4-phase mixers will up convert all the odd harmonics, the fundamental, the third, the fifth, the seventh, and so on. But the relative phase of those harmonics is different. So what we see is that as in a normal 8-phase mixer, the harmonics that actually get back to the RF port are just your fundamental and then starting with the 7th harmonic and above. So we get our classic 8-phase improvement in terms of harmonic radiation and therefore improvement in loss. And the 3rd and 5th harmonic, however, are that overlap path. So another way of looking at the overlap effect is instead of thinking of it as sort of charge sharing between adjacent paths, you can think of it as interaction of a different set of harmonic sidebands. In this case, the 3rd and the 5th harmonic sidebands are basically shunting each other. And by putting those inductors in there, I basically suppress that shunting and therefore reduce their effect. So we can model this out using the same framework as before. We can say we have now our source impedance now has some inductance in it because we put those inductors into the circuit. We now actually have 2 transistors on at all times, and so our effective switch resistance is actually lower. But now we have our two shunting impedances, the harmonic shunting and now this overlap shunting. And we can compute the values of those. They're those same sorts of infinite sums we saw before, but now they're operating on different sets of harmonics. Now, the neat thing is if we just do some simple math on that, we see we can actually predict the series impedance, the overlap shunting impedance, and the harmonic shunting impedance. And what we notice is that there's a region where the series impedance is still low, but both the overlap and the harmonic shunting impedances have gotten much higher and therefore dramatically reduced our loss. So we can just check how this really works in simulation. So here what we're doing is we're just basically, first we look at the 25% duty cycle case and see what noise figure we predict across a frequency range. And we see it's less than 3 dB. We go to 25% duty cycle, we immediately get that overlap and we take at least a 3 dB hit in our noise figure just coming out of the blocks. If we add an appropriate value inductor in there, we basically knock our noise figure back down to where we were before almost exactly. And if we were to get the inductance wrong, if we were to be too low by a factor of 3 or too high by a factor of 3, we can see that, unsurprisingly, that impacts our performance at either the low or the high end of our frequency range. So we actually built this and tested it. The circuit works from about 2 to 8 gigahertz, so 2 octaves of range. It's mostly fairly standard circuits, but now, again, 25% duty cycle, which is much easier to generate with frequency dividers, and then those interleaved inductors. And what we see immediately is that we get the expected noise figure improvement. So across that frequency range, our noise figure is below 5 dB the whole way, and indeed, in part of that range is below 3 dB. Whereas if we'd been only 4-phase, if we sort of go into a 4-phase mode, we see at least a 2 to 3 dB noise figure degradation relative to that. So the 8-phase properties are doing what we want, and they're also avoiding all the overlap effects we were worried about. We're still able to get harmonic rejection. It's not great in this design because our 45-degree splitting was a little bit hinky at the high frequency end of range of things, but we also still preserve our good linearity. So our out-of-band linearity is still sitting in the 20 dB, multiple 20s, or like in this case 28 dBm out-of-band IP3, and compression points that are on the order of +5 to +10 dBm, very similar to what we had before without all those inductor tricks. We've also realized that we can apply the same idea for 4-phase mixers, but the thinking is a little different. So we started out with our standard 4-phase mixer, right? We've said before that we use we know that overlap causes leakage between essentially now the I and Q paths, and we normally beat that by having 25% duty cycle. However, that's really hard to do at high frequencies. Indeed, at very high frequencies, we'd rather be using a sine wave. And if we do use a sine wave, then we have to worry about all that overlap. And so the insight that Zach Boynton, who did this work, had was that if he inserted a transformer between the I and Q paths, he could actually suppress this effect. And there's a couple of different ways of looking at why that suppression works. But it turns out that the most useful way to look at it is to think about, again, what is the sort of sideband associated with the leakage? So it turns out what you have, if you look at a 2-phase mixer, you down convert the signal. When you re-up convert a 2-phase mixer, you get both the signal back and also the image of the signal. But critically, between I and Q, the relative sign of the signal relative to the relative sign of the image is different. And so what I get now is essentially a shunting of the image, and that overlap effect is exactly the same as the image loss. Those are essentially the same phenomenon. And I should say that we had this insight, we were really proud of ourselves, and then we discovered it actually had been discovered more than 10 years ago by Ahmed Mirzai and his colleagues at Broadcom. So, nothing new under the sun, but it's still a really important insight. It just basically tells you that the problem of overlap is the equivalent to another sideband. In the 4-phase case, the other sideband is your image. So now putting the transformer in there, the reason that works is that it presents it basically brings the signal in as essentially like a differential signal to the I and Q. So therefore, it basically acts as an impedance transformer for the signal, but for the image now appears as a common mode, and the transformer presents a high impedance to the image, and therefore suppresses it and reduces that loss. So we did a first design in 65 nanometer CMOS, which is a bulk CMOS, which is maybe a little slow for the frequencies we were working in, from 8 to 32 gigahertz. But the key thing we saw is we still got okay noise figure. It's a little higher than we'd like, but a better process would improve that. And again, the very good out-of-band linearity, now tuning across, again, about 2 octaves, but now in the millimeter wave frequency range. Okay, I have one last thing to talk about, and then I'll be done. And that's to ask a sort of a different question, which is, and this is the chip we did to test this, is how could we maintain a pulsed LO at millimeter wave frequencies? Could we go up to sort of 20 to 40 gigahertz and still use essentially our more standard 25% duty cycle approach without burning crazy amounts of power to do it? And so we had two insights for this. The first is to recognize that actually, from a maintaining good switching perspective, HBTs are better than CMOS. And so if we can make HBTs work, we would have a better sampling waveform. And the second is a trick we call a dual resonant LO, which I'll explain in a moment. So now, obviously, the problem with using HBTs is they don't have that switch property of normal mixers. But we know we can make mixers, or no, not normal, of the N-path CMOS approach. But we know we can make mixers. So we can think about this. We bring in an RF current. We basically turn on a sequence of BJTs in series that down converts the current to baseband, generates a voltage just as before. But we have no mechanism for that voltage to get re-F converted to the RF port and present its impedance there. So that's the down conversion path. However, if we add some feedback back from the baseband port to the base of the transistor, what we see now is that the base impedance, the base node where the LO is coming in is now going to be riding on top of that baseband signal that's being fed back. And critically, the peak voltage we see, which will drive the actual voltage on the emitter of the transistors, is now tracking that summation. So if we look at the actual emitter voltage, we see that emitter voltage now has a re-F converted version of the signal, and therefore gives us impedance transparency. So it turns out you can actually build N-path filters using HBTs using this feedback technique. Now, I'm going to gloss over this a bit, but when we first did this, we used resistors for feedback, and it turned out that has a significant noise penalty. However, if you use essentially an emitter follower for your feedback, it has a nice set of properties that basically mitigate this. And I refer you to our RFIC paper from last year to see the details of this. Now, the second trick we wanted to bring into play is what we call dual resonance. And the starting point idea of this is you say, if I'm building a pair of coupled inductors, I can actually give that coupled inductors different resonant frequencies for the differential and common mode. Particularly, if I make the coupling coefficient minus 0.6, I can make the common mode resonate at twice the frequency of the differential mode. Now, why is that useful? Well, if I think about how I'm going to generate my pulsed waveforms, if I just have the fundamental, I get a sine wave, which is not a remotely non-overlapping waveform. However, I also include this common mode second harmonic. When I sum up the differential fundamental and the common mode second harmonic, I get a much more pulse-like waveform, as I'm showing at the bottom here, which is much more suitable for an N-path-like approach. So we've actually built a full receiver using these techniques, including the feedback technique, the dual resonant LO buffer, and we actually also included a noise-canceling auxiliary path, following on work done by again Mirzai et al. Some years ago. Actually, Murphy was the lead author on that. And here, the main idea is that your main mixer core, gives you the impedance transparency and things, but also tends to have a certain amount of noise associated with it. Your auxiliary path essentially measures that noise and adds a little bit from its LNTA. But if you do your sort of circuits appropriately, you can essentially cancel out the noise from the main path and have only the noise from your LNTA. So your noise gets better, but at the same time, the linearity and the filtering properties of the main path act to protect the auxiliary path. So if you just had the auxiliary path, it would be unprotected. But if you have them both on, you get this sort of noise enhancement from having the auxiliary path, but a linearity enhancement from the protection from the main path, and you get a better system overall. I'll skip ahead. So we built it. So if we actually measure this system, what we find is that when everything's working together, we can tune from 20 to 40 gigahertz. We get a noise figure of about 9 dB, which is not great, but not bad given the frequency we're at and given that we have that we're doing such a wide tuning range. We also get really good out-of-band linearity. We have about a plus 9 dB B1 dB out-of-band blocker tolerance. And we can also show that all these techniques we are using works. So for example, if we turn off the main path, so we just have the auxiliary path, we still have good noise figure because that's still dominated by the LNTA, but our linearity gets way worse because we've lost the protection of the N-path filtering. Conversely, if we turn on only the main path, we get the great linearity back, but now the noise figure is degraded because we have all the extra noise of the main path without the LNTA protecting it. And then if we turn those both back on, but turn off our dual resonant technique so that we're using sine waves instead of the pulsed waveforms, we see that both linearity and the noise get worse, which is essentially consistent with the mixing waveforms being worse and effectively our rho being degraded. Okay, so in conclusion, and then I'll be done, N-path mixers and filters have become a core element in modern RFIC circuit design, particularly in conjunction with LNTAs. They allow for useful filtering and flexibility. They have great out-of-band linearity and generally acceptable noise. And they act as an enabling component for many new interesting systems. So not just mixers, but also for circulator-like things and for various filter concepts and so on. At this point, the fundamental limits and trade-offs are fairly well understood. That's a lot of what I talked about. And we clearly see that performance degraded at higher frequencies, but it kind of in new ways than we're used to in classic small signal systems. So that harmonic loss aspect and the overlap loss really matter, and they involve all the harmonics as being important. But we are seeing a new wave of topology innovations coming through that are pushing both the dynamic range and the frequency, so it's still a moving target. And so overall, I'd say that N-path mixers are here to stay, but there still has a lot of that space still has a lot of new things going on, and it's a major area for more new circuit innovations in this space. With that, I want to acknowledge the various students who were involved in all the parts of this project, as well as my collaborators and my funding agencies. And if you're interested, I can give you a list of exciting papers to read about this. There's lots and lots of interesting literature. With that, I'll stop. And I'm happy to take questions.
Sure. Thanks, Professor Molnar. This was very good talk, and we were happy to attend this talk with you. You walked through with us through from like very simplified versions and what are the insights, and then going deeper and deeper, and going through at the very last the like some tricks, I would say, to minimize the effects and pushing the limits for the passive mixers. We may have time for few questions, maybe one or two max. So one question is, compared to active mixers, do you think that the passive mixers or N-pass can be pushed for millimeter wave, or what do you think about that?
I think they can. I think, I mean, I'm certainly trying to push them for that. I think one way I've looked at the N-path passive mixer space is that it tends to trail the sort of cutting edge of active circuits by like 10-ish years. So, right now, most millimeter wave is active for all the same reasons that most sort of low RF was active in the late 90s and early aughts. And the passives are passive mixing, and N-path sort of takes over both as the process gets better, but also as we figure out how to account for its additional sort of requirements and limitations. So I think it's got a good shot. I think one important thing to note is that there's actually, in the basic N-path thing, there are sort of two distinct phenomena that are being used. One of them is the passivity, which gives us the impedance transparency and therefore the really high linearity, which we can also do in BJTs with the right feedback. And the other phenomenon is the actual sampling waveforms being not 50% duty cycle. And so we can separate those two and sort of attack them separately. So for example, I think at millimeter wave, there's a good bet we're gonna, at some point, have to surrender the pulsed waveforms. They're just too hard to generate, or at least the general purpose pulsed waveform. But conversely, if you can generate them, you can also use them in active mixers. So a 25% duty cycle active mixer is better than a 50% duty cycle active mixer for quadrature. And so I do think they have a future in millimeter wave, but I think it's probably, it's going to be delayed by 10 years because it's just that much harder. There's that much more to do to make it work.
I see. Okay, thank you. I think one last question that we have, what is the effect of the self-resonance frequency or SRF for inductors that you have in your slew rate, like cancellation?
Yes, that's a very good question. So what basically comes out of it is that, of course, the inductors only look like inductors to some frequency, and then they look like capacitors. For the 8-phase case, what basically happens is the inductors improve your suppression of those sort of overlap harmonics up to some point, and then they look inductive. But even when they look inductive, the impedance still may look higher for a watt for some range of frequencies than it would have without the inductor in there. So basically, for any frequency range where that including the inductor makes the impedance look higher, then those harmonics will be reduced. And because it turns out that the lowest harmonics matter the most by far, like the third and the fifth, as long as your self-resonance is above, say, the fifth harmonic, you get most of your benefit. In fact, as long as it's at or above your third harmonic, you get at least half your benefit right there. But it certainly does limit you. So we're actually exploring using those at millimeter waves now, and it's like dealing with the resonant and sort of self-resonant effects is definitely a critical piece to optimizing it, and you don't get quite as much of a win.
I see, and also I think it will also affect the kind of the delay for each pass. Like what you showed us is 2 passes like that. So this one and this one will be rotated from each other now.
Well, so what
they had, at least at the fundamental, a little bit.
So what we definitely see is that the fundamental is rotated relative to the input because there's just some additional delay from that resonance. The key is if those mixers are identical, the fundamental sees them as just in parallel, and so the delay is equal to both the I and the Q.
I see.
And the main question is how they interact with each other. And in that context, once you go past self-resonance, it gets a little weirder. What mostly happens though is once you get past self-resonance, basically the rather than the shunting, like the overlap getting you directly, it just goes back to just harmonics leaking into the parasitic capacitance. So you're just losing power to the parasitics directly, and that's kind of reverts to the more basic math.
I see. Noise figure bad, and then losses, and
everything just makes everything worse. And so again, the main thing is to try to suppress as many harmonic sidebands as you can. And so the lower ones being more important because they're stronger. So if you can just get rid of the third, if you can just suppress that one, you already get a pretty big win.
Yes, yeah. Okay, would like to thank you again, Professor Molnar, and we'll be happy to see you in person hopefully soon. So with that, we are concluding.
Thanks for having me. And anybody, if you have other questions for me, I'm easily found on the internet on Cornell's websites, and you can send me an email and ask questions. I'm happy to answer. So thank you.
Thank you very much.
Thank you, Professor. Thank you, everyone. Bye now.